Hello friends, today we are going to learn types of excitations. Now, sigma sigma star excitation. When electron transfers from bonding molecular orbital sigma to higher energy sigma star antibonding molecular orbital is called as sigma sigma star excitation. All saturated compounds indicates sigma sigma star excitation. We can take the example of alkanes. All alkanes are saturated and it contains only single bond, that is sigma bond, and therefore alkanes indicate sigma sigma star excitation. Second type of excitation is N2 sigma star excitation. When electron transfers from lower energy non-bonding molecular orbital to higher energy sigma star anti-bonding molecular orbital is called as N2 sigma star excitation. The compounds containing single bond between carbon atom and heteroatom like oxygen, nitrogen and sulfur indicates N2 sigma star excitation. We can take the example of alcohol, amines. This type of compounds indicates N2 sigma star excitation. Third type of excitation is pi star excitation. When electron transfers from lower energy pi bonding molecular orbital to higher energy pi star antibonding molecular orbital is called as pi star excitation. The unsaturated compounds containing carbon-carbon double bonds or carbon-carbon triple bond indicates pi star excitation. We can take the example of alkenes and alkynes. This contains carbon-carbon double bond and therefore they shows pi star excitation. And fourth excitation is N2 pi star excitation. When electron transfers from lower energy non-bonding molecular orbital to higher energy pi star antibonding molecular orbital is called as N2 pi star excitation. The compounds containing double bond between carbon atom and heteroatoms like oxygen, nitrogen, sulfur indicates N2 pi star excitation. We can take the example of ketones, acid, aldehydes. This contains C double bond O group and therefore they indicates N2 pi star excitation. Next point is terms involved in UV spectroscopy. The first term is chromophore. It is an unsaturated functional group which is capable to absorb UV radiation is called as chromophore. We can take the example of carbon-carbon double bond, C double bond O, NO2, etc. All these are the unsaturated functional group and therefore they are able to absorb the UV radiation and therefore they are called as chromophores. We can take the example benzene ring. In case of benzene ring, there is presence of unsaturated functional group, that is carbon-carbon double bond, and therefore it is able to absorb the UV radiations at 255 nanometer. Similarly, in case of ethylene, there is also presence of carbon-carbon double bond, that is unsaturated functional group, and therefore it is also capable to absorb the UV radiation at 170 nanometer. The next point, that is oxochrome. So what is meant by oxochrome? It is saturated functional group which does not capable to absorb the UV radiation is called as oxochrome. We can take the example OH, NH2 and Cl. These are the saturated functional groups and therefore they are not capable to absorb the UV radiations. But when oxochrome is attached to chromophore, then oxochrome is capable to absorb the UV radiation. We can easily understand from the example. Now, when benzene is alone, at that time, benzene absorbs UV radiations at 255 nanometer. But when this benzene chromophore is attached to OH oxochrome, then absorption takes place to higher wavelength, that is 270 nanometer. Means this increase in lambda max is due to attachment of oxochrome OH. So in short, remember that when oxochrome is alone, at that time it does not absorb the UV radiation, but when OH oxochrome is attached to chromophore benzene, then OH oxochrome is able to absorb the UV radiation, and therefore the lambda max value increases, that is 270 nanometer. Then next point is bathochromic shift, that is also called as red shift. When absorption takes place to longer wavelength, called as bathochromic shift or red shift. We can take the example of phenol. Phenol shows bathochromic shift or red shift in presence of alkali. When alkali is added to phenol, then this OH group abstract the proton and we get the phenoxide ion. At first, phenol absorbs at 270 nanometer. But when alkali is added to phenol, then absorption takes place at 287 nanometer. The increase in lambda max is due to effective delocalization of negative charge of oxygen as compared to lone pair of electrons of OH group. Now in this case, the chromophoric length increases and therefore the lambda max also increases in the phenoxide ion. The next term is hypsochromic shift, that is also called as blue shift. When absorption takes place to shorter wavelength is called as hypsochromic shift or blue shift. Example, aniline shows blue shift in presence of acid. At first, pure aniline absorbed at 230 nanometer, but when aniline reacts with acid, then absorption takes place at 203 nanometer. Means absorption decreases. When aniline reacts with HCl, then the electron pair of nitrogen abstract the proton, therefore nitrogen becomes electron deficient, it carries positive charge. The decrease in lambda max is due to the formation of positive charge on nitrogen atom. So electron pair of nitrogen is not available for the delocalization in benzene ring. Therefore, the conjugation decreases and therefore lambda max value also decreases, that is 203 nanometer. The next term is hyperchromic shift. Hyper means high, large. In hyperchromic shift, the increase in molar absorptivity takes place. And the last term, that is hypochromic shift. Hypo means less. A decrease in molar absorptivity is called as hypochromic shift. In short, in hyperchromic shift, molar absorptivity increases, but in case of hypochromic shift, molar absorptivity decreases.